Hey y'all, Data Guy here. And today I have a video for you that I thought would be helpful for just anyone kind of exploring networking in general. And that is explaining synchronous and asynchronous networks, showing you their, kind of just breaking down exactly what they are, their pros and cons, their use cases, and then give you a framework for comparing and contrasting them and give you, think, hey, which one is right for my particular use case? So without further ado, going to get into this and really just break down and help you understand what synchronous and asynchronous networks are. So let me know if you like this video in the comments below, and like and subscribe too if you do. But without further ado, let's go. So within the realm of just computer networks and data communication, the distinction between synchronous and asynchronous networks is just foundational for how you think about a lot of different systems, and that's kind of why I wanted to make this video. And they represent really different approaches to managing the timing and coordination of data transmission between nodes. So what we're going to do is compare and contrast exactly that, synchronous versus asynchronous networks. So first thing we're going to cover is synchronous networks, and I want to just dive into exactly how they work and some of their pros and cons. So with synchronous networks, they're really characterized by the presence of a clock signal that will coordinate all data transmissions. And that clock signal ensures that the sender and receiver are synchronized at the bit level, allowing data to be sent at precisely timed intervals. And just to quickly show you what a clock signal is, that is literally just a mechanical kind of or electronic tool that every set period of time sends a signal out. So you see the waves in the graph, it goes up to 5 volts to signalize it's on, and then it turns off after, let's say, a second. So that is what we're referring to when we're talking about clock signals. And then, so that clock signal, the key feature of the synchronous network is that its reliance on the shared clock signal to control the timing of all communications. So both the sender and receiver are both listening to the same clock. And this means that data can be sent continuously without the need for intermediate start and stop bits. So because you have that shared clock that's just managing the flow of information, you don't need to have any other intermediary mechanism to actually handle that. So some of the benefits of this design, number one, efficiency. Because data is sent continuously without pauses, there's no need for an external service to say, hey, stop, then start sending data. Because they're just listening to that clock signal, the synchronous networks often are able to achieve higher throughput compared to asynchronous networks. And then also the predictability. The presence of a clock signal makes the behavior of the network predictable, which is crucial for applications that require tight timing control, like real-time monitoring systems. And then there's also really good error detection, just naturally built in to synchronous systems because they use predefined frame structures that can include error-checking data, therefore enhancing the actual reliability of the synchronous transmission. Now, on the downside of things, so number one is complexity. The need for actually having that clock that's synchronized between these two systems and is signaling both of them at the same time can add complexity to the network design and also increase the cost of your infrastructure. And then also scalability. Maintaining clock synchronization across a large network, or maybe you would have hundreds of these different data pipelines, or even thousands. You got to maintain then 1,000 different clock synchronizations. And it's going to be very challenging if you don't have a really good system and plan for that and implement it. And then finally, susceptible to clock failure. So one single point of failure that can break the entire network is if the failure of the clock mechanism. So you need to make sure that that is really hardened and robust and has good alerting and failure rollover mechanisms so that it doesn't just blow up your entire network just because a clock signal has actually failed. So that was synchronous networks. Now it's time to talk about asynchronous networks. And so asynchronous networks operate without a centralized clock. You can sound asynchronous versus synchronous. It's pretty much the complete opposite, where instead data is transmitted using start and stop bits to indicate the beginning and end of a transmission. So you can see that in this example here where there's the start bit, 0, and then the stop bit, 1, to say, hey, the transmission has started, so receiver, listen to the transmission, and then the 1 bit telling the receiver to turn off and no longer listen to that transmission. And so this method allows the receiver to synchronize with the sender at the beginning of each data piece independently, which makes it suitable for environments where data is sent sporadically. Every once in a while, this receiver receives a piece of data, rather than a synchronous network where you have almost a continuous stream of data. And so the pros of this are simplicity and flexibility. Asynchronous networks are easier to implement and then also maintain because there's no need for clock synchronization across the entire network. They're also much more cost effective. These networks generally will require less infrastructure and also are cheaper to set up and operate because you don't need to have that clock signal running and also transmitting it to both the sender and receiver. And then also it's a bit more robust than synchronous networks because asynchronous transmissions are less affected by synchronization issues, which makes it, again, better in environments with high interference or varying signal delays or really just any kind of unexpected interference that could affect that clock signal, where a synchronous network, that could take down the entire network. Now, on the negative side of things, you have lower efficiency. The use of these start and stop bits introduces potential overheads because you just need to emit that command, which reduces the effective data rate. Obviously not by a huge amount, but it is additional data that you need to transmit. You also have variable latency, so the absence of synchronization can lead to variable delays in data transmission, which might not be acceptable if you need an actual real-time application. And then also complexity in error handling. So error detection and correction are generally more complicated because you have variable packet sizes, you don't have a common clock, you have data transmission starting and stopping at any time, and so you basically have to track down through the actual bit code, the start and stop bits there. So can be just a little bit more, obviously, kind of goes in hand in hand with, it's less error prone, but when errors arise, it's going to be harder to figure it out because you don't have that single point of failure with the clock, but instead have a few more different ways where it could go wrong. And so use cases, asynchronous networks are suitable for applications where data is transmitted intermittently or where the network might not support continuous connectivity, so distributed sensor networks, email transmission, general internet data traffic. You only need to send that data when someone wants to connect to a website. And so those are just some of the general use cases that you would want to use asynchronous versus a synchronous network for. But now I want to kind of get into a more formal comparison mode, so switch over and start giving ourselves a framework and talk about the differences and pros and cons of using one or the other. So here I've kind of put up a graph comparing synchronous and asynchronous networks to help visualize what the difference is and how they approach data coordination and timing. So with a synchronous network, because you have just that one continuous stream of data where it's you have one sender, one receiver, and you just are on that clock where, hey, data is transmitted, then it stops. Data is transmitted, then it stops. Data is transmitted, then it stops. And so the clock is just syncing that up based on that timing. And so here you can kind of see the disadvantages of that approach versus a synchronous network, where here we have just one completes in 20 seconds, then another completes in 7 seconds, then another completes in 10 seconds, then another completes in 8 seconds. And so the difference here is that with asynchronous networks, because you don't need to have it linked to that clock, you just have to tell the receiver with that bit of 0 saying, hey, start accepting data. You can actually have multiple sources importing data into that system at the same time. So in the example here, instead of it taking 45 seconds to complete these 4 tasks, by allowing you to perform them in parallel, you can actually get the same amount of work done in only 20 seconds. And so that's really the key difference in how how these two networks are set up. Synchronous networks offer efficiency and predictability at the cost of complexity and susceptibility to clock issues, and really only being stuck on that kind of linear track. Yes, you can set up multiple synchronous networks to transmit those same 4 tasks in parallel, but it's, again, you got to maintain 4 clocks. It's just going to be more difficult. But it does make them suitable for really high throughput, single-threaded, real-time applications where it's just continuous stream of data, just like we just had one task that goes on forever. However, asynchronous networks, on the other hand, better flexibility and cost efficiency, maybe less adherence to and less time-sensitive applications, so less suitable for those, but allows you to do things like upload data in parallel, not be just restricted to that single-threaded nature. And so when you're thinking about deciding between a synchronous and asynchronous network, you should really consider the following factors. Number one, data transmission requirements, the continuous versus intermittent data transmission. your timing sensitivity, your need for real-time data handling versus tolerance for delays, scalability needs, so small controlled environments versus large dispersed environments. Think about which one is best for each. Obviously, asynchronous for large dispersed, synchronous for small controlled. And then budget constraints. If you have to do a lot of different tasks at the same time and you're not able to pay for all those clocks to set them up, probably going to want to go asynchronous. It's probably going to be a bit cheaper, and also just be easier to maintain. And then finally, reliability and robustness needs. So susceptibility to interference and signal variability. If you're dealing with the potentialist problems, you're probably going to want to go with asynchronous networks because they'll be able to handle that kind of variability much better versus that might just completely break a synchronous network. And so, in summary, synchronous networks preferred when timing and throughput are critical. Asynchronous better for simplicity, flexibility, and better for when you just need to move a lot of different data. So hope this video has helped you understand both of these approaches, understand synchronous versus asynchronous and which one might be best for your particular use case. And I hope you have a great rest of your day. Data Guy out. Peace.